Hi everybody, hope you're doing well. We're continuing with our acids and base chapter, and this is part 2. And so last time we talked about Arrhenius acids and bases and also Bronsted-Lowry acids and bases. And we talked about acids being H plus donors and bases being H plus acceptors. And that's the Bronsted-Lowry definition. The Arrhenius definition was, if you put an acid in water, it gives away H pluses. If you put a base in water, it gives away OH minuses. So how about water? Water is said to be amphiprotic. The prefix amph means that it's both. So like amphibian means it's both living on land and in water. Amphiprotic or amphoteric mean the same thing. That means it's both an acid and a base as well. So it turns out that water very mildly autoionizes. What does that mean? That means that water by itself will very slightly ionize, will turn into ions. So you can look at this here. You take a molecule of water, and a tiny bit of that will ionize into H plus and OH minus. It's an equilibrium, but the equilibrium lies towards the reactants, reactant favored. So most of the water remains as liquid water, molecular water, but very few molecules will ionize, turning into ions H plus and OH minus. So if we look at this, according to the Arrhenius definition, we are giving off H pluses, which means it's an acid. We're also giving off OH minuses, which means it's a base. Or, if you prefer, you can look at this equation here. So you have two water molecules here, and what could happen is, let's say this water molecule behaves like an acid, and this molecule behaves like a base. So an acid, according to Bronsted-Lowry, is a proton donor. So if this gave away an H plus, it becomes OH minus. And if this is a base, that means it accepts a proton. So if this took the H plus from this one, then it becomes H3O plus. And so a proton donor and a proton acceptor, which makes it both an acid and a base. Again, this is an equilibrium, but it lies towards the left side, and so most of the water stays as molecular with very little ions forming. It's not enough ions that it can even conduct electricity. It's not detectable. So if you take distilled water and put a conductivity tester in there, it will show that it's negatively it's not conducting electricity. So the ions that you form here are very small amounts. They're negligible. Most water stays as molecular. So if I wanted to write the equilibrium expression for either one of these, H3O plus and H plus mean the same thing. They just mean, a proton. H plus in water makes H3O plus. So those, again, mean the same thing. Hydronium ion or hydrogen ion mean the same thing. So let's, just for simplicity, look at this one. So if I wanted to write the KQ expression, the equilibrium expression, remember from last chapter, you write the concentrations of the products over the concentration of the reactants raised to the power of the coefficients. And so you would write KQ is equal to the H plus concentration raised to the first power times the OH minus concentration raised to the first power. We do not divide by the concentration of the water. Why? Because it's a liquid. We do not include it in the equilibrium expression. No liquids or solids. So this is the equilibrium expression for the ionization of water. However, because this is a special process, not just any reaction or physical process, it is the ionization of water, which is a pretty special process. We give it its own special name. And so instead of just calling it K or KQ, we call it KW. So KW is equal to the concentration of H plus times the concentration of OH minus. What does that KW stand for? It stands for the water dissociation or ionization constant. Let's write that down. So it is the water ionization constant or the water dissociation constant. They pretty much mean the same thing. So at room temperature, 25 Celsius standard temperature, the ion product constant for water, which is the same thing as water ionization or dissociation constant for water, Kw, at room temperature is equal to the concentration of H plus times concentration of OH minus, we said, and that turns out to be 1.0 times 10 to the negative 14. Remember, K is a constant if you are at a certain temperature. So at 25 Celsius, which is room temperature, the Kw for water is 1.0 times 10 to the negative 14. That's a number that you need to remember. Turns out, any aqueous solution, whether it's acidic, basic, or neutral, so not just water, any aqueous solution, if you take the concentration of the H plus in that solution times the concentration of the OH minus in that solution, it is always equal to 1.0 times 10 to the negative 14. Again, any aqueous solution, acid, base, or neutral. Now, if you have a neutral solution, or if it's water, which is neutral, in any neutral solution, including water, the H plus and the OH minus concentrations are going to be the same. If you look at water, for every water molecule, you get one H plus and one OH minus, right? That every water molecule that ionizes, you get one H plus and one OH minus. So the H plus and the OH minus are equal to each other. Every time I make an H plus, I have to make an OH minus, right? So those two concentrations are equal to each other. So if we're saying that Kw is equal to the H plus times the OH minus concentration, and that is equal to 1.0 times 10 to the negative 14, we can solve for what these are. So if we say that the H plus concentration, let's say, is X, the OH minus concentration would also be X, right, because they're equal to each other, and X times X is equal to Kw, which is 1.0 times 10 to the negative 14. So this is X squared. So if you take the square root of both sides, you get X is equal to 1.0 times 10 to the negative 7th molar. So in water, or any neutral solution, the H plus concentration is equal to the OH minus concentration, which is equal to 1.0 times 10 to the negative 7th molar. That's a pretty small number. That means that the concentration of my ions is 0.000000, 1. Erase that real quick. So in a liter of water, you have 0.000001 moles of H plus or OH minus. That's pretty small. That's really negligible. So again, this happens very, very little. Most of the water remains as liquid molecular water. Very, very tiny amount of it ionizes. So what if I take my water, where my H plus and OH minus concentration are equal, and they're both equal to 1.0 times 10 to the negative 7th molar, and I add acid in it, in that water. Well, the acid, when you put it in water, gives off H pluses and whatever the conjugate base is, A minus. So if it was HA, it'd be H plus, and A minus are the products. How much this goes depends on whether it's a strong or a weak acid. So a strong acid means that it fully ionizes or fully dissociates. So HA is molecular, right? They're sharing the electrons, like HCl, for example, they're sharing electrons. When you put it in water, magic happens and it turns into H pluses and Cl minuses, for example. If it is a strong acid like HCl is, that means it fully turns H plus and A minuses. So it goes 100% to completion. The equilibrium lies to the right. So again, with something that is a strong acid, that means it fully ionizes, fully turns into ions. So the HCl, all of it turns into H plus and Cl minus. However, if it's a weak acid, that means it barely ionizes or dissociates. Very little of it actually turns into ions. HF, for example, is a weak acid. So that means if I take some HF and put it in water, only a tiny bit of it turns into H pluses and F minuses. The majority of it remains as molecular HF. So that's the difference between a strong or a weak acid. A strong acid fully ionizes, turns into ions. So all of it turns into the ions. I don't have any of the molecular acid left when I put it in water. Something that is weak, most of it remains as the molecular acid in a very, very tiny amount of H pluses and F minuses form. So with HCl, we say the equilibrium lies to the right because it's product favored. With a weak acid, the equilibrium lies to the left. That means it's reactant favored. I have mostly reactants at equilibrium. There are six strong acids. All other acids are weak. There are, thousands of different acids. Only 6 of them fully dissociate 100%. The other ones are weak, which means they partially dissociate or ionize to different extents. Let's list the 6 strong acids. So we have HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3, which is nitric acid, HClO4, perchloric acid, and then H2SO4. Only first H plus is strong. What does that mean? That means that, remember, this is diprotic, which means it can give off 2 H pluses, right? So first it can give off H plus and HSO4 minus, and then the HSO4 minus can give off an additional H plus and SO4 2 minus. So the first one goes to completion to give off an H plus. The second one is weak. It's an equilibrium. Similarly, there are some strong bases and weak bases. So a strong base means it fully ionizes or dissociates, goes 100%. A weak base partially ionizes or dissociates to give off OH minuses. So the strong bases are group 1 and group 2 hydroxides. What does that mean? For example, NaOH or CaOH2. So any metal that's from group 1 or group 2 bonded to hydroxides would be a strong base. That means 100% dissociates. So something like NaOH fully 100% dissociates into Na plus NOH minus. So that would be strong base. Something like aluminum hydroxide that only partially dissociates into Al3 plus and 3OH minus, because that would be a weak base. Okay, now, we said that if you take an acid and put it in water, so if you take water, you have H pluses and OH minuses equal to each other. You have 1.0 times 10 to the -7th molar of each. Let's say you take acid and put it in water, it gives off H pluses. So now my H pluses increase. I have too much H pluses, right? More than this number. But when I multiply those two, I always get 1.0 times 10 to the -14th. So that means if I have more H pluses, that means that I'm going to have less OH minuses. So that's what this is saying here. So if you look at this, if I put an acid in water, it gives off H pluses. So that means the H plus concentration is bigger than this number, right? So the H plus concentration is higher than the OH minus concentration, which means the H plus concentration is higher than 1.0 times 10 to the -7th molar. Similarly, if I take a base and put it in water, remember bases either give off OH minuses or take in H pluses, right? And so let's say we look at the Bronsted-Lowry definition where it's a proton acceptor, so it takes in H pluses. So if I have water where both of these are equal to each other and I put a base in there, it takes away some of the H pluses. So my H plus concentration is lower than my OH minus concentration, which means my H plus concentration is lower than 1.0 times 10 to the negative 7th. So based on the concentration of the H plus, I should be able to figure out if it's an acid or a base. So if it's neutral, both of these would be equal to 1.0 times 10 to the negative 7th. If it's acidic, that means my H plus would be higher than this number, my OH minus would be lower. So acid means extra H pluses, less OH minuses. If I have a base, that means I have less of the H pluses and more of the OH minuses. So my H plus is less than this number, my OH minus is higher than this number. So a base means I have more hydroxides, less H pluses. So H pluses, lots of H pluses means it's acidic, lots of OH minuses means it's basic. If they're equal, that means it's neutral. So just based on that, you should be able to predict whether it's an acidic or basic or neutral solution. For example, let's say I tell you my H plus concentration is equal to 1.0 times 10 to the negative 5th molar. Is the solution acidic, basic, or neutral? Well, what you do is you compare this number with what it should be if it was neutral, if it was water. Which number is bigger, 10 to the negative 5th or 10 to the negative 7th? Yep, this is much bigger. So that means I have a lot of H pluses compared to neutral. So that means this solution is acidic. What if my H plus concentration was 9.2 times 10 to the negative 11th molar? So again, you compare this number to 1.0 times 10 to the negative 7th. Which number is bigger? This number, right? This is much smaller than 1.0 times 10 to the negative 7th. So that means I don't have a lot of H pluses. I have very few H pluses, which tells me this is a basic solution. Let's look at the OH minus concentration. What if my OH minus concentration is 5 times 10 to the negative 4th molar? What does that tell me? This number is bigger than that 1.0 times 10 to the negative 7th. So that means I have a lot of hydroxides compared to what it would be at neutral. Lots of hydroxides means that it's a basic solution. Let's do one more. What if my hydroxide ion concentration was 2.6 times 10 to the negative 9th molar? Let's see. This number is much smaller than 1.0 times 10 to the negative 7th. So that means I don't have very much hydroxides compared to neutral. So that means that it's acidic solution. So again, you should be able to look at just the concentration of either the H plus or the OH minus and be able to predict if it's acidic or basic or neutral. Now, looking at these numbers though, our brain can't really comprehend these numbers very well, right? You know, this is 0.00001, 0.005, and, you know, 0.10 O's and then a 9. It's just really hard for us to really look at these numbers and kind of comprehend them easily. And so because of that, they came up with something called the pH scale. I know you've talked about the pH scale before. The pH scale is a scale that measures the acidity or basicity or neutrality of a solution. And some people say that the pH scale, the P stands for power. When I took math in Egypt, we learned that P, lowercase p, means negative log. So like, you know, in math, independent of the science class, we would say like, you know, the function of A is equal to this. What is PA? And so we knew that P means negative log, so you take negative log of function A, whatever it was. So mathematically, pH is equal to the negative log of the H plus concentration. That's what pH stands for. So if you look at any solution, we said if you take the H plus times the OH minus concentration, that's equal to 1.0 times 10 to the negative 14, and that's equal to Kw. In a neutral solution, like water, the H plus is equal to the OH minus concentration, which is 1.0 times 10 to the negative 7th molar. So in water, if I want to calculate the pH, we said pH is equal to negative log of the H plus concentration. So it's equal to negative log of the 1.0 times 10 to the negative 7th, which is equal to 7. That's why the pH of neutral solutions is 7. In an acidic solution, the H plus concentration is higher than that of the OH minus concentration. So the H plus concentration is higher than 1.0 times 10 to the negative 7th. If you take negative log of a number that is bigger than this, it's going to be a smaller number than 7 because it's negative log, not just the log. So in an acidic solution, the pH is less than 7. In a basic solution, the H plus concentration is less than the OH minus concentration. It is less than 1.0 times 10 to the negative 7th molar, and so the pH is greater than 7. And I know that you've studied logs in math class before, but I know a lot of you forgot how to do logs, and so we'll practice that on the next slide in a minute so that these numbers make more sense to you if you forgot how to do it. Now, you're probably familiar with pH. pH is equal to negative log of the H plus concentration. And so let's go ahead and start with that. So let's look at the next slide. And so I have a bunch of concentrations of H plus here, and I'm going to first try to figure out what the pH is equal to, okay? So when you are trying to find the pH, obviously you can just plug it into your calculator. You know, if I give you 1 molar as your H plus, the pH is equal to negative log of the 1, right? So you plug that into your calculator, find out the answer. Now, that is okay to do with harder numbers, but I would like you to be able to do or find the pH of these just by looking at them. You should be able to do that in your head. So how would you do that? What you do is you write your number as 1 times 10 to some power. So if I want to write 1 as 1 times 10 to some power, this is the same thing as 1 times 10 to the negative, or 1 times 10 to the 0, right? 1 times 10 to the 0. Now, if you write it that way, logs are powers of 10, right? Logs are powers of 10. So if you look at the power of 10 here, negative of that number is your pH. So negative 0 is 0. Let's do the next one. 0.1 is the same thing as 1 times 10 to the negative 1. Right? So logs are the powers of 10. And so you do, if you want negative log, that means negative of this number. So negative 1 is positive 1. Let's look at the next one. 0.01 can be written as 1 times 10 to the negative 2. So again, log means power of 10. So if I take log of this, it would be negative 2. Negative log of it would be negative of negative 2, which is positive 2. Next number. This is the same thing as 1 times 10 to the negative third. So negative log of that would be 3. Next one, 1 times 10 to the negative 4. So negative log of that would be 4. This one, already written for us in this format, so negative 6 would be positive 6. This one would be 7, 11, 12, 13, and 14. Look at that. Something with 1 times 10 to the negative 7th molar, which is neutral, right? Neutral would be pH of 7, at least at room temperature. Something that is more acidic, so these numbers, right, these molarities are bigger than this number. So these are acidic. All of these here are acidic. Look at their pHs. Their pHs are less than 7. The lower the pH, the more acidic it is. So I'm going to go ahead here and write most acidic. Now let's take a look at these. These numbers are much smaller than this at neutral, right? So less H pluses means that it's basic. So these are basic solutions. Their pHs are higher than 7. Again, because we're taking negative log, not just log. And so this one, out of all of the examples we have, this one would be the most basic. The higher the pH, the more basic it is, or the less acidic it is. Now, another thing to note when it comes to pHs, again, we're looking at logs, which are base 10, right? They're the powers of 10. So that means a change in 1 pH unit is equivalent to 10 times the concentration. If you compare 1 to 2, a change in 1 pH unit is 10 times the concentration. So a change in 2 pH units, going from 0 to 2, that's 100 times the concentration. A change in 3 pH units would be 1,000 times the concentration, and so on. So a change in 1 pH unit, that's significant. That's, again, 10 times the concentration of the H+, or a change of 2 units is 100 times. So a small change in the pH really means a huge change in the concentration because it's log base 10. Now let's look back at the previous slide. Now, just like we figured out that pH is equal to the negative log of the H+ concentration, there's no reason to single out H+, right? Water has equal amounts of H+ and OH-, so how come the H+ gets all the love? You've probably heard about the pH scale, but you haven't heard about the Poh scale. And so in chemistry, again, H+ and OH- are equal, so there is no reason why to do it in terms of H+ and not OH-. So P, we said, was negative log, so POH would be negative log of the OH- concentration. Just like pH would be negative log of H, POH is negative log of OH-. So let's take a look back at let's stay on this here for a second. So this third equation is something we've talked about on the previous slide, right? H+ concentration times OH- concentration for any solution is equal to 1.0 times 10 to the negative 14. So now let's look at the next slide here and see if we can figure what the H+ or the OH- concentration would be given the H+. So let's try this here. I'm going to write the equation on the top. So I wrote this equation, H+ times OH- concentration is equals to Kw, which is 1.1 times 10 to the negative 14. If you rearrange this equation to solve for the OH-, OH- is 1 times 10 to the negative 14th over the H+ concentration. So now let's plug in these H+ concentrations so we can figure out what OH- is. So let's say that this is 1 down here, right, for the first one. What would the OH- concentration be? It's going to be 1 times 10 to the negative 14. Okay, now let's plug in the next one. What if the H+ concentration was 0.1, or 1 times 10 to the negative 1? So what if this was 1 times 10 to the negative 1? What would the OH- here be? Remember, when you do this, you subtract the exponents, right, when you're dividing, and so that would be equal to 1 times 10 to the negative 13. Okay, let's move on to the next one. What if it's 0.01, 1 times 10 to the negative second? So let's say this was -2 instead. Again, you subtract so the exponents, so you get 1 times 10 to the -12. Next one, this one is -3 now. So that would be 1 times 10 to the -11. These are molar, I forgot to put the units there. Okay, next one, what if this was a 4 here? So make that 4. What does that equal to? 1 times 10 to the -10th molar. Next one, 1 times 10 to the -6. So now this number is a -6. That would be So that would be 1 times 10 to the -8th molar. Let's do the next one. The next one is 1 times 10 to the -7th. So go ahead and erase this one and do -7. So what would that be? That would be 1 times 10 to the -7th molar. Next one, -11th. So when you divide that, you get 1 times 10 to the -3rd molar. Next one is -12. So 1 times 10 to the -2nd, which is the same thing as 0.01. Next one would be 1 times 10 to the -1, right, which is 0.1. And this one would just be 1 times 10 to the -0, which would be 1 molar. So now let's look at these and note a couple of things here. We can make it a little smaller. There we go. Now notice that the higher the H plus concentration, the lower the OH minus concentration, right? So here H plus is really high, here the OH minus is really small, and vice versa. When the H plus is really small, the OH minus is really big. So the smaller the H plus concentration, the higher the OH minus concentration, and then vice versa, right? Notice also that when it's an acidic solution, the H plus concentration is higher than 1.0 times 10 to the -7th. The OH minus concentration is lower than 1.0 times 10 to the -7th. When it's a basic solution, the H plus concentration is lower than 1.0 times 10 to the -7th. The OH minus concentration is higher than 1.0 times 10 to the -7th. And then notice that when it's neutral, look at this, neutral solution, both concentrations are 1.0 times 10 to the -7th. That's where it's neutral and they're both equal to each other. Now, we said that just like we can get the pH is the negative log of the H plus concentration. POH would be negative log of the OH minus concentration. So let's try it together. If I take negative log of this, that would be negative of the -14, which would be 14. Next one, POH would be 13. Next one, 12, 11, 10, 8, 7, 3, 2, 1, and 0. Notice that the POH is the opposite of the pH, right? The lower the pH, the higher the POH. The higher the pH, the lower the POH. Notice also that when it's neutral, both of them are 7. So an acidic solution has a low pH and a high POH. A basic solution has a high pH and a low POH. A neutral solution has both of them equal to 7. Now notice also if you add up the pH and the POH, it equals to 14. 0 plus 14 is 14. 1 plus 13 is 14. 2 plus 12 is 14. 3 plus 11 is 14. 4 plus 10 is 14. 6 plus 8 is 14. 7 plus 7 is 14, and so on. When you add the pH plus the POH, it is equal always to 14. Now take a look at this equation again, right here. Let's say you take negative log of this equation. Negative log of H plus is called pH. Negative log of the OH minus is called POH. When you have two numbers that are multiplied, you take the log of that, you add them. Negative log of 1.0 times 10 to the negative 14 is 14. You get this equation. pH plus POH is always equal to 14. Isn't that cool? So these 6 equations that are in bold here are the equations that you need to know and be able to use. So all we did on this slide right here is just more for understanding, to realize what does it mean to have a certain pH or a certain H plus concentration or OH minus concentration and so on. So we have kind of covered all of these 6 equations that you need to use. Let's talk briefly again about them. So first one, pH is equal to negative log of H plus. I think most people already know this. This one is the same exact thing as this, except you put OH instead of H. So if you know this one, you should know that one. This one we know from the last slide, so you need to memorize this one. If you know this one, you can figure this one out, right, by taking negative log of this. These two are the inverse logs. Inverse log is 10 to the power. So if I am given the H plus concentration, I'm trying to find the pH, I do negative log of the H plus concentration. But what if you're given the pH and you're trying to find the H plus concentration? Well, you do 10 to the negative pH. Same thing with this one. If you're given the POH and you're trying to find the OH minus concentration, you do 10 to the negative POH. So you need to be able to use these 6 equations, but really, if you know this one, you can come up with that one and these 2 as well. If you know this one, you should be able to come up with that one. So really, I think for me as a student, I would have probably memorized this one and this one and came up with the other ones from them. If you don't like that, if you don't like to derive these equations from each other or think through them, you can just memorize all 6. So now we're going to use the 6 equations to calculate some stuff. So these are calculations that we can use for strong acids and bases. Why only strong acids and bases? Because when we're given a strong acid or base, we know it goes 100% to completion. You'll see that in a few examples as we go. So number 1 says, given a solution where the H plus concentration is given to you as 1.0 times 10 to the negative 9th molar, we want to calculate the OH minus concentration for the solution. So we're given H plus, we're trying to find OH. Which equation would you use? You would want to find an equation where you have H plus and OH minus in the same equation. So that would be this equation right here. So I would rewrite this equation down here, and I would plug in my numbers. So this is 1.0 times 10 to the negative 9th times the OH minus concentration is equal to 1.0 times 10 to the negative 14. Can you do that in your head? You would take this number divided by this number. So you subtract the exponents. So this gives you that the OH minus concentration is equal to 1.0 times 10 to the negative 5th molar. Next, we want to calculate the pH of the solution. So we would want to use this equation right here. pH is equal to negative log of the H plus concentration. So it is equal to negative log of 1.0 times 10 to the negative 9th, which is 9. And then finally, we want to calculate the POH of the solution. There's different ways to do that. You could, since we have the pH now, you could use pH plus POH equals 14. You could also use this equation, POH is equal to negative log of the OH minus concentration, now that we have the OH minus concentration. Either one, either this one or this one would work. I'm going to go ahead and use this one. So pH plus POH equals 14. So that means that 9 plus the POH equal to 14. So POH is equal to 5. If you had used this equation right here, POH is negative log of this, that would still give you 5. So you'd still get the same answer. Let's look at number 2. It says calculate the H plus concentration for a solution where the OH minus is given to you, and then it's asking is the solution acidic, basic, or neutral. So I'm looking for the H plus concentration. I have the OH minus, so I want to look for an equation that has both of these two variables in there, and so I want to pick this equation again. So I'm going to rewrite that, and then you want to plug in your numbers. The H plus concentration times 4.3 times 10 to the negative 8th is equal to 1.0 times 10 to the negative 14. Now, at this point, you would want to plug that into your calculator, take this number, divide by that number. However, you should always kind of have an idea about what the number should be. So, your number should be, somewhere in the vicinity of 10 to the negative, 6 or so, close to that. Now, if this number was 1 times 10 to the negative 8th, it's going to be 1 times 10 to the negative 6, right? But it's a bigger number than that, so it should be actually maybe something to the negative 7th. But what I mean is, like, you kind of know the vicinity of where your answer should be. So let's go ahead and plug it in and see what our answer is. Let's see, H plus concentration ends up being 2.3 times 10 to the negative 7th mole. Again, if it's a concentration, make sure that you have your units there. Second part asks, is this acidic, basic, or neutral? And there are multiple ways that you could do that. You could look at your H plus concentration. You could look at the OH minus concentration, see if it's higher or bigger than the negative 7th. You could find the pH, you could find the POH, so there's a variety of different ways. No matter which way you pick, you're going to get the same answer, but the problem is if you look at different ways, you might confuse yourself. So I recommend, since you're all familiar with pH, just stick with pH, find the pH for that. If you find the pH for this number, it should be 6 point something, which tells you it's slightly acidic. Again, you could do it different ways. If you're pretty confident, you could look at this and say, oh, this number is bigger than 1.0 times 10 to the negative 7th. I have lots of H pluses, so that is acidic. So again, no matter what method you pick, you're going to get that it's acidic, but just so that you don't confuse yourself, maybe the best method is just always stick with pH. Let's look at question number 3. It says calculate the POH for a solution where the OH minus concentration is given to us, and we want to know if it's acidic, basic, or neutral. So I have the OH minus concentration, and I want to find the POH. So you want an equation that has those two things in it. So that would be this equation here. So let's rewrite it. POH is equal to negative log of the OH minus concentration. So negative log of 1.2 times 10 to the negative 6. Again, you're welcome to go ahead and plug it into your calculator, but try to kind of have a sense of what your answer should be. So, if this was just 1.0 times 10 to the negative 6, then your answer should be 6. So it should be close to 6, but not quite. Maybe you're slightly lower. So go ahead and calculate it. You end up with POH equal to 5.9, and that's our answer. It's asking if it's acidic, basic, or neutral. Again, you can do it in a variety of ways. You can say, oh, POH is low, so that means that it's basic. Or you could say, oh, this number is higher than 1.0 times 10 to the negative 7th, which means hydroxides are high. That means it's basic. Or best bet is find the pH. So pH would be 14 minus 5.9. which would be 8.1. 8.1 would be basic. So any of those methods would tell you that it is basic. Let's look at question number 4. It says calculate the POH for a solution where the H plus concentration is given to us. And again, is the solution acidic, basic, or neutral? So we are trying to find the POH, and we're given the H plus. So let's look at our equations. What equation has those two different variables? Well, none of them. What does that mean? That means that you have to do 2 steps. So there's different ways to do this. I'm trying to find the POH and I'm given the H plus, right? One way to do this is to use this equation. Since we're given the H plus, we can use this equation to find the OH minus concentration. Once we find the OH minus concentration, we can then plug it in here and find the POH. That's one method. Another method is to use this equation. Since we're given the H plus, we can find the pH. Once we find the pH, we can then use this equation to find the POH. Both methods are just as good. They'll give you the right answer. I think the second method is a little bit easier. Addition and subtraction is easier than multiplication and division. So let's go with the second method where we're going to use the H plus concentration to find pH, and then from the pH, find the POH. So I'm going to use this equation first. So pH is equal to negative log of the H plus concentration. So negative log of 2.5 times 10 to the negative 5th. That ends up being a little less than 5, 4.6. And then I'm going to say pH plus POH is equal to 14. So 4.6 plus the POH is equal to 14, which means the POH is equal to 9.4. So that's our answer. Is this acidic, basic, or neutral? You can look at a variety of different things, but probably the easiest way is just always stick with the pH. pH is 4.6, so that tells us that it's acidic. Again, you could look at this and say, oh, this is a high number compared to 1.0 times 10 to the negative 7th, so that is acidic. No matter what way you do it, you should find out that it is acidic. Let's look at question number 5. It says, calculate the H plus concentration if we're given the pH. So for this one, we want an equation that has pH and H plus concentration. So let's look at those two here. This one you use if you're looking for the pH. This one you use if you're looking for the H plus. They're inverse equations of each other. So I'm going to go ahead and use that second equation. So H plus concentration is equal to 10 to the negative pH. So that's 10 to the negative 5.2. Now you can't leave this just as is. You actually have to punch it into your calculator and find what the answer is. So the answer is 6.3 times 10 to the negative 6 mole. Again, if it's a concentration, make sure that you have your units. Let's look at the next one. So the next one says we have a solution that has a pH of 9.4. We want to calculate the OH minus concentration. So we are going to look for an equation that has the pH and the OH minus concentration. So looking through these 6, we don't find any that have both pH and OH minus concentration. We don't have any that have those two variables. And so what does that mean? Yep, that means that we are going to do 2 steps. So as always, multiple ways whenever you have to do 2 steps. One way is to, from the pH, calculate the H plus concentration by using this. So the H plus is equal to 10 to the negative pH. Once we have the H plus concentration, we can use this equation. If we have the H plus, we can find the OH minus concentration. That's the first method. The second method, since we have the pH, we can find the POH by using this equation. So we have the pH, we can solve for the POH. And then once we have the POH, we can use this equation to find the OH minus concentration. Again, I prefer the second method because adding and subtracting is easier than multiplying and dividing, but both methods will get you the same exact answer. So I'm going to go with the second method, which is from the pH, I'm going to find the pOH by using this equation. So I'm going to say that pH plus pOH is equal to 14, which means that 9.4 plus the pOH is equal to 14, and that gives me a pOH of 4.6. Next, I'm going to use this equation here, which is the OH minus concentration is equal to 10 to the negative pOH. So this is equal to 10 to the negative 4.6. And again, I can't leave it like that. I have to actually plug it in. And I get 2.5 times 10 to the negative 5th molar. And that is my answer. Just for fun, is the solution acidic, basic, or neutral? Different ways to do it. Easiest way is just stick with pH. So this would be basic because it's higher than 7. Let's look back at number 5. We forgot to look at number 5. Let's see this one, acidic, basic, or neutral. Again, stick with pH. This would be acidic. Doesn't ask you, but this was just for fun. All right, let's go to number 7 next. So number 7 says calculate the pH of 0.004 molar HCl solution. So where do we start? It doesn't really give us any of these variables, right? It asks for pH, but all it says is that we have a solution that's HCl and it's 0.004 molar. So let's think, HCl is what kind of solution? Well, it's an acidic solution. And what type of acid is HCl? Well, it's one of the 6 strong acids. So what does that mean, that it's strong? That means that it dissociates or ionizes 100%. So let's write the equation for what happens when you take HCl and put it in water. You take HCl, put it in water, you get H plus and Cl minus. And again, this is one of the strong acids, which means that you 100%, one arrow, go to completion. So all of the HCl ionizes into H plus and Cl minus. So if I had 1 mole of HCl, then that means I'd end up with 1 mole of H pluses and 1 mole of Cl minuses. What if I had 2 moles of HCl? I'd have 2 moles of H plus and 2 moles of Cl minus. What if I had 0.004 moles per liter of HCl? Then I'd get 0.004 molar of this one and 0.004 molar of this one, right? Every single one of these molecules turns into 1 H plus and 1 Cl minus. So if I start with 0.004 molar of this, that means I end up with 0.004 molar of this and 0.004 molar of Cl minus. So what does that tell us? Well, that tells us the H plus concentration right here. And so basically they're telling us what is the pH if our HCl concentration is 0.004 molar. So we're given H plus concentration, we're trying to find pH, we just use this equation. So, excuse me, pH is equal to negative log of the H plus concentration. So it is equal to negative log of 0.004, which gives me 2.4 is my answer. Now, why did I bother to even write this out? Well, a couple of reasons. And with this one, you could have just gotten lucky and just did, negative log of that would be your pH. But what if you were given NaOH instead of HCl? So what if right here this said NaOH? What would you have done differently? Well, you would have said NaOH is a strong base as opposed to acid, right? And so because it's strong, it dissociates 100%. But what does it turn into? Na pluses and OH minuses. So then this would be 0.004 molar. This would be 0.004 molar. This would be 0.004 molar. What would be the difference? Well, this is your concentration of hydroxide, not of H plus. So if I take negative log of that number, that would be my POH, not my pH. So you got to watch out, write your dissociation equation to figure out, do you get H pluses like here, or do you get OH minuses like here? A second reason you want to write out your dissociation equation is if, especially with bases, let's say instead of NaOH, what if it had said it's 0.004 molar calcium hydroxide? How would that be different? Well, you'd say, oh, calcium hydroxide is a strong base, dissociates 100% into calcium 2 plus and 2 OH minuses. So if this was 0.004 molar, this would be 0.004 molar. But this one would be 0.008 molar because this is a 1 to 2 ratio. For every 1 calcium hydroxide that you put in water, you get 2 OH minuses. So you got to watch out for that. So whenever you're given a strong acid or a strong base, I want you to write the dissociation equation or the ionization equation for it. And that way you can be sure what is the concentration of either the OH minus or the H plus. All right, there is a worksheet that helps you practice all these calculations. Please work on that and let me know if you have any questions. Hope you have a great rest of your day.